So I want to continue talking about functions, and I'm going to do something somewhat easy or maybe familiar to a lot of you, and then I want to do something that's probably more difficult and maybe not familiar to many of you. So I'm going to start with the more difficult stuff. So we say a function f, which takes elements from the set A and maps them to the set B, is injective or one-to-one, which we often write 1-1, which looks like a smiling Bomberman from the video game Bomberman. If every element in the range is associated to a unique element in the domain. That is to say, if no two inputs have the same output. So we know for something to be a function, each input has to have exactly one output. Now we're saying this is a special type of function where each output has exactly one input, right? We don't have two things mapping to the same output. An injection, that is a function that is injective, will pass the horizontal line test that is the graph of the function will touch no horizontal line more than once. So this is a lot like the vertical line test. So the vertical line test, if the graph of your function touches no vertical line more than once, then it's a function. If a graph touches a vertical line more than once, then it's not a function, it's just a relation. If a graph touches no horizontal line more than once, then in addition to being a function, it's a special type of function called a one-to-one function or an injection or an injective function. Right? Now there's a sort of a secret code. So f is one-to-one if and only if the following holds. F of A equals f of B implies A equals B. Okay? So how do I read this? F is one-to-one implies that if two outputs are the same, then the inputs had to be the same. Similarly, if every time that I have f of A equals f of B, that implies A was actually equal to B, this is the same as saying each output has a unique input, and that implies f is one-to-one. Okay? That might take some practice, so you'll see some examples of that as we move forward, but for now, just this is sort of the secret code for one-to-one. All right. F is called surjective or onto. So there's this word onto, which in this case, I just cannot make the top of that thing not curl. Onto is an adjective in this case. If the range is the whole codomain. That is, if every element of the codomain is mapped to by f. So we can say f is onto, here's the sort of symbolic way to say it, if and only if, for all b in B, there exists a little a in A such that f of a equals b. So this is kind of the symbolic way to say f is onto. Okay, so this is the symbolic way to say f is 1 to 1. This is the symbolic way to say f is onto. All right. Finally, we say f is bijective, or a 1-to-1 correspondence if it is 1-to-1 and onto. I don't really like this term 1-to-1 correspondence because we already say 1-to-1 for something, and sometimes people call a function a correspondence or talk about corresponding elements, and this is its own thing, but I just feel like it's a little bit murky linguistically. So I prefer the term bijection. F is bijective, it is a bijection, whatever, if it's 1-to-1 and onto. So that's what I'm gonna try to stick to that language, even though this is also acceptable language. All right, so let's do some examples of functions that are 1-to-1 or onto or not. So first, let's have f of x equals x cubed. Then we'll have g of x equals x squared. Then we'll have h of x equals x cubed minus x. All right, so x cubed is going to look kind of like this. And this is going to be 1-to-1 and onto. All right, now how do I know that? Well, if I look, any horizontal line that I draw across this function is never going to touch the graph more than once. Now here, it's tangent, if you know what that means, but it's only going to be at one point. I can check this by saying, suppose f of a equals f of b. Actually, let me do this in a little bit smaller type. This is one of the reasons I like this program. I like to zoom in. Suppose f of a equals f of b for inputs a and b. Well, that implies that a cubed equals b cubed, but that implies that a equals b, right? If I take the cube root of a real number, I get the same thing back. And if this doesn't totally make sense yet, that's all right. We're going to compare it to the companion calculation for g of x, and then hopefully this will make a little bit more sense. Moreover, this is onto because every possible y value is an output, right? Every possible y value is used, so this thing is onto. Now, if that doesn't totally make sense, that's okay. Let's move on, and let's sketch a graph of g of x. Oh, and I did it again. We're just going to assume each of these maps R to R. Okay, this is actually important. Just for demonstrating 1-to-1 and onto. Because sometimes if we're using a different domain or different range, then we can have a function, like I can come up with a special domain and range for x squared that makes it 1-to-1 and onto, but this domain and range, it's not going to be 1-to-1, and it's not going to be onto. So not 1-to-1, not onto. And why is that? Well, x squared is going to have a graph that looks like a parabola. And when we go after the horizontal line test, okay, here horizontal lines are fine. Right here at x equals 0, it's fine. But now each of these horizontal lines hits the parabola in more than one point. So it fails the horizontal line test. Moreover, we're not using any of these values. So so why is this not 1-to-1? Well, it fails HLT, the horizontal line test, but we could also, so I can just say, fails HLT, but I can also check, what if f of a equals f of b? And this is sort of the companion calculation to this one, like I said I was going to do. If, sorry, not f, what if g of a equals g of b? Well, that implies that a squared equals b squared, which implies that a equals plus or minus b, by taking the square root of both sides, but it does not imply that a equals b. In fact, I have that g of, let me bump the button again, g of 1 equals 1 equals g of negative 1, but 1 doesn't equal negative 1. So this thing's not on, it's not 1-to-1. Now it's not onto because it misses the negatives. That is, the real numbers is the codomain, and there are real numbers, namely, let's say -1, that are never mapped to by this function x squared. -1 is not the square of any real number, right? So there are elements in the codomain, there are elements that are in the correct format of the output that are never mapped to, that are never actual outputs of this function. So it is not onto. Okay, finally, let's do h of x mapping reals to reals is x cubed minus x. We're not going to do a whole lot of factoring in this class, but let's just do it for fun right now. This is x times x squared minus 1, and x squared minus 1 factors into x plus 1, x minus 1. So this has zeros at 0, at -1, and at +1. So we've got 0 at 0, +1, -1. And then if we know a little bit more about polynomials, we can see that we're going to have a graph that looks like this. And what do we know about this function? Well, this function, if we check the horizontal line test, it's fine up here, it's fine down here, but anywhere in the middle here, it's going to fail. This function is going to fail the horizontal line test, implying that it is not 1-to-1. Okay? Big X for 1-to-1. However, we can see that every possible output is attained. I mean, this line, this curve goes all the way down, it goes all the way up. So every possible output is attained. So range equals codomain implies that it is onto. Okay, so we have a function that is, a function that's 1-to-1, a function that's onto, a function that's not 1-to-1, a function that's not onto. We've seen a few different things. And so that, probably some of you are now saying, well, do there exist functions that are 1-to-1 but are not onto? So we've got functions that are both. We've got functions that are neither. Now we've got a function that is onto but not 1-to-1. So here's a fun exercise. Find a function that is 1-to-1 but not onto. So while you think about that, let's do, so I would consider that kind of the harder part of this section. And now let's kind of slow things down and do what I'm going to call the easier part of the section. Again, not to say that it's easy, but just you may have seen this before, or maybe it's not as difficult. I'm going to talk about floor and factorial. So the factorial, function takes natural numbers and 0 as inputs. You could also say the whole numbers, and gives natural numbers as outputs. And it is given by n factorial equals n times n minus 1 times n minus 2 times ... times 3 times 2 times 1 for any natural number n, and 0 factorial equals 1. Now it might seem weird. You might want to say, well, shouldn't 0 factorial be 0? It might make sense that way initially, but the more you mess with factorial, the more it makes sense for 0 factorial to be 1. And there are a few different reasons for that. I mean, number one, just the formulas that we come up with using factorial, we would have to have all these special cases for 0 if we didn't just say 0 factorial is equal to 1. Another argument is that the factorial function lines up with this other function sort of called the gamma function. And with the way that you would get information about factorials from the gamma function, we would expect that 0 factorial is 1. And so you can Google the gamma function if you'd like. That's kind of fun. But we won't be going into that in this class. And finally, since this is a largely computer science-based class, I want you to think of this as a for loop that doesn't execute. So if I had a for loop that was doing that was summing, and I was saying, for I equals 1 to 100, total equals total plus I, or whatever it is, then if that for loop didn't execute, nothing would be added to total. And so if we, depending on the language, let's suppose you didn't initialize it, then the default value might be 0, it might not, but if we're trying to total something up and that addition never happened, then we're going to have the default value of 0. I want you to think of this as like a multiplicative totaling, or a multiplicative for loop, and I want you to think of this like a bonus multiplier on like a pinball machine or something. So if you get the bonus lights, then the bonus multiplier is like it multiplies by 2, multiplies by 3, whatever. But if you don't have a bonus multiplier, it doesn't mean you get no points. It just means you multiply your score by 1, or you just get your score with no bonus. Next, the floor, or sometimes called the greatest integer function, takes real numbers as input and outputs the greatest integer less than or equal to the input. Okay, this is just rounding down. Depending on your programming language, you might have something called ipart, or to convert to an integer, it might just chop off the so-called fractional part or chop off the decimal. And this is just going to take whatever your real number is and remove the fractional part. So let's do some examples of these. 4 factorial is going to be 4 times 3 times 2 times 1, which is 6 times 4, which is 24. Let's do 1.1. Oopsie daisy, I didn't even tell you what the notation was. Denoted floor of x. It's like square brackets, but without the top. Okay, that's floor. Let's do floor of 1 point. Gosh darn it, I drew the whole bracket on there. Let's do floor of 1.1, floor of 1.9, and let's do floor of negative 1.1. Okay, floor of 1.1 we round down to 1. Floor of 1.9, put a box around my answers. Floor of 1.9, again, even though if we were just rounding, we'd round up, floor means you always round down, so this rounds down to positive 1. And floor of negative 1.1, we round down, not closer to 0, so this is going to be negative 2. All right, so hopefully that makes sense. I guess what do I owe you? A function that is 1-to-1 but not onto. So here's a function that's 1-to-1 but not onto. E to the x is 1-to-1 but not onto. There are others. So that was fun. Okay, hope this made some sense. Please feel free to pause